Well, dear students, we are again back to this lecture number 28 in the series of mechanics of metal forming. So, last time we took certain examples after formulating the upper bound method of limit analysis. In this lecture we would continue still few more examples and applications based on certain applications of upper bound theorem. So, let us start with an example here which is shown in figure 13, and this case again it is plane strain extrusion with frictionless square die. So, as you know, in case of extrusion we have a ram and there is a die, and when we extrude in cold condition the ram pushes with certain velocity, and from the die a proper reduction takes place and product comes out. So, this figure 13 is considered as the plane strain extrusion with frictionless square die. Square die means there is no conical die like, and there are no other dies. So, square die means the section is cut in a plate whatever to be extruded, the geometry. So, let us start with this example to demonstrate how a pseudo independent variable can be incorporated in the velocity field, and subsequently it is used to optimize the kinematically admissible velocity field to minimize the power, which is our ultimate goal for forming. So, look at this figure 13a where this a initial starting shear lines has been shown. So, this is what is the extrusion chamber, and the point C, point A and point B. B is the corner of the die, C is at the center line of the extrusion, and A is at the exit point, the closest exit point at the die. And please note that before point C the ram is pushed with velocity which is equal to 1 unit velocity, as it is the requirement of the upper bound, and after extrusion the velocity comes out at V, which is faster and which is more than 1. And please note this shear line, that is AC and BC. The AC makes an angle theta and BC makes an angle phi, and based on this one can draw the hodograph for this sheet extrusion where a very small reduction is going to take place. So, this hodograph is drawn similarly as it was explained earlier. So, one can, so now you mark the region. So, again here region 1, region 2 and region 3. Within this triangle A, B, C, this is region 2, and after it comes out then region 3, and the billet when it enters, so that is the region 1. So, correspondingly one can mark point 1, 2 and 3. So, if let us start with the O, that is the U is equal to 1 unit, taking 1 unit one can draw is here, and then it is parallel to the first discontinuity line BC, and then this one is at an angle which is phi. So, this is, you note down the first discontinuity line with horizontal, it is phi, and the second discontinuity line, that is AC, is at an angle theta. So, this has been shown parallel, drawn parallel, and that gives velocity v. Wherever it cuts, let it, that is the velocity v to be found it out. So, using these two equations and consider the discontinuities velocity field, where the velocity discontinuities are along BC and AC. So, as shown in this figure, the material to the left of velocity discontinuity line is moving to the right with unit velocity, and input thickness of the sheet is, say, HI, capital HI, and output thickness, say it is HO, capital HO, if it is. So, the reduction R would be equivalent to the ratio of input to the output thickness. So, the hodograph for the velocity field as suggested is shown completely in 13b. So, from the proposed velocity field, it is clear that theta is the only variable for given input and output thickness values. The proposed velocity field indicates that the material travels parallel to the horizontal boundary of the die till it reaches the velocity discontinuity line BC, and then suddenly it starts flowing parallel to the vertical surface of the die till it reaches the velocity discontinuity line AC, and then suddenly it starts flowing parallel to the horizontal line. So, keeping this way, if you recall equation number 15.6 earlier, the upper bound, the inequality, so that gives the upper bound solution for plane strain deformation with rigid blocks movement. As you see here, the rigid block region 1, region 2 and region 3 here also. So, assuming the material to be rigid, perfectly plastic, the power P, capital P, required to extrude the material can be written. So, it can be written, if you use the hodograph, that is capital P would be equal to K multiplied by the because there are two velocity discontinuity BC and AC. So, it is equal to K multiplied by capital B, capital C, and velocity from the hodograph, that is U BC, plus capital A, capital C, U AC, and by geometry then it can be substituted the value of BC and AC, and similarly from the hodograph geometry one can substitute the value of UBC and UAC, then the P becomes is equal to K multiplied by 1 by cos phi multiplied by HI divided by sin theta, plus second term as K multiplied by HI multiplied by H0 divided by H0 cos theta sin theta, and then this can be simplified as HI K multiplied by 1 plus R multiplied by 1 plus R tan square theta and whole divided by tan theta, and this simplified value has been shown in equation 64 therefore. So, you know that R is the ratio, that is the reduction ratio, which is defined as HI by HO as explained earlier. So, here the only unknown variable is theta, and the power required to extrude can be minimized by differentiating with respect to theta therefore, and therefore that gives the P minimum. So, P minimum would be what? It would be 2K 1 plus r hi divided by under root r. That has been shown in 65. So, if the pressure required to extrude the material is small p and the ram is moving at a unit velocity, so one can say that p hi multiplied by 1, that is the velocity unit, must be less than or equal to what has been calculated as p minimum, and that is nothing but 2k 1 plus r hi divided by root r, and thus one can calculate that p by 2k is less than or equal to 1 plus r divided by under root r. So, this inequality, that is p by 2k, is less than equal to the right side, which is shown here in equation 67, is the solution, upper bound solution. So, that now that p minimum can be used for designing the process. Now, let us take another example where the extrusion through a smooth circular die is taken as. Earlier it was a flat die, now let us take another case where the smooth circular die is taken. So, this figure is shown here in figure 14a and b the corresponding photograph. So, because the earlier example had straight boundaries, if you look into, the discontinuity had been straight, but in this example it has a curved boundary. So, as shown in figure 14a, the input material, the thickness is 1 unit and the ram is pushing the material into the die at a unit velocity, as usual we had been doing. So, if the reduction in thickness is taken as 50%, say, the die radius will be 0.5 units, because we have taken the width as thickness as 1. So, as shown in figure 14a, so one can see here that the material is entering at unit velocity and the reduction is 50%. So, look at carefully here the geometry as well. So, the discontinuity becomes across the curved boundary AB and curved boundary BC, and accordingly the straight path has been shown as dotted, and that shows the angle theta. So, one can see here HB is 1 and therefore HA is 0.5, and when the velocity, initial velocity is 1, the final velocity becomes 2 because the height is reduced to half, and correspondingly photograph is shown here in that is the photograph for extrusion through a smooth circular die having radius r as 0.5, it has been shown. So, the exit velocity has to be 2 units to satisfy the incompressibility condition or kinematically admissible conditions. So, it is assumed that there is no dead metal zone, however, in this process. Earlier there was a dead metal zone, but it was assumed that there is no effect of the dead metal zone, and therefore in this case the velocity discontinuities, that is AB, BC and AC, are assumed to be circular. So, here AB and BC have the same radius and AC has a radius of under root 2 multiplied by 0.5 and the center is at point B. During extrusion, the compressed material will flow parallel to the chamber boundary till it encounters velocity discontinuity AC, and then it will follow a path which is parallel to the die surface till it crosses the velocity discontinuity BC. And after BC, the material flow will be parallel to the axis. So, the hodograph, if you draw for the proposed velocity field, it is shown here in 14b. One can note down that the material to the left of AC, that is the block 1, will be moving at unit velocity, and the material to the right of BC will move at velocity equivalent to 2 units to satisfy the kinematically admissible field. And so, the velocity discontinuities along AC and BC will be causing the material to gain the velocity from 1 unit to 2 unit. This is quite obvious, and the extrusion power, therefore capital P, required for this operation can be obtained by using the upper bound theorem as usual, as is been explained, for rigid perfectly plastic material, and that is the equation which was previously given in equation number 56. So, if you apply equation number 56 for this particular case, the curve boundary is calculated, that is the power, extrusion power would be equal to K multiplied by arc AC multiplied with the velocity, that is UAC, plus arc BC multiplied with the velocity, that is UBC. And if you in the terms of extrusion pressure small p, the above expression that is which is shown here in 68 can be written as, that means P by 2K is equal to half of the arc AC multiplied by UAC plus arc BC multiplied by UBC, which is determined from hodograph figure 14b. So, if one substitute the values from figure 14, one can get after measuring from the hodograph and after measuring the arc AC total length, etc. So, if you substitute, one can get P by 2K, that is equal to 3 by 8 pi, and this is what the solution expected. So, this example shows all these examples so far we discussed for plane strain, and that is how we assume the velocity field as well as hodograph 2D, 2 dimensional. When we use the upper bound solution for 3 dimensional case, then it becomes more complicated, and so let us take few more examples for 3D case, and this time let us assume axisymmetric extrusion, because if we take axisymmetric 3 dimensional extrusion, still we can take it on 2D. So, let us take this figure number 15, where the application of upper bound technique is used using a continuous velocity field. Earlier the velocity field was not continuous. So, now here if we take continuous velocity field method for axisymmetric problem through this particular example 15, figure 15, here the deformation zone is assumed to be bounded by straight plastic boundaries, that is S1 and S2. You can look at the end section of the extrusion die, the material outside the entry and exit section is assumed to be right to be rigid, totally rigid, and therefore the axial velocity at the entry and exit section of the die should be uniform. So, if you look at this figure, the whole domain is shown with a streamlined surface where the domain and this is the S1, S2 and S3, these are the three surfaces. S1 the entry, S2 is the S3 is the die surface, and S2 is the exit, the end of this one. And this is what's the die geometry is a streamlined now. So, this is what is assumed one. So, the initial radius at entry is r1, the velocity is v0, and here r2 and velocity would be v. So, these now the z direction is along here and r direction is upward. So, there is another streamline which keeps the ratio, extrusion ratio same, and therefore, there is a xi is a factor which is multiplied by r1 and xi is again multiplied by and the r2, and rx is the geometry of the streamlined surface. So, using these conditions, one can write down that Vz, that is the center line, is the velocity is v0, that is on surface S1, and using the incompressibility condition, Vz becomes onto the surface 2, if it is calculated, it must be equal to, if you use the incompressibility, it must be equal to V0 multiplied by R1 square divided by R2 square, because the radius R1 entry and R2 exit, where V0 is the ram velocity, as I said. There should not be any metal flow, however, across the boundary S3 and across the axis of the symmetry. That means V normal, if I define Vn as V normal, that is 0. So, on the die surface S3, the axis of symmetry is assumed. So, that is the axis of symmetry. So, the die surface S3 and the axis of symmetry Vn is 0. So, the die profile and the axis of symmetry must be streamlined, as I said, as the normal velocity is 0 along the die surface and at the exit of symmetry. It is further assumed that the axial velocity profiles at the end section are uniform, and additionally it is assumed that the flow pattern in the deformation zone can be represented in the same functional form as the die profile. So, under these assumptions, equality spaced streamlines at the die entry remain equally spaced at the die exit as well. So, therefore, the streamline in the deformation zone can be given as that has been shown here in equation 74, and therefore, that is nothing but r multiplied by xi r z. So, r z is the function where the xi is represents a streamline with value that ranges from 0 at the exit to 1 at the die surface, and Rz, as I said, represent the die profile. So, this die profile can be third order, it can be second order, it may be many other. So, it can take the place of conical die, it can be take place as the cosine die, etc. So that is the beauty of 3-dimensional case. So for axisymmetric flow, one can assume the stream function, that is psi, which is there, as a continuous nth order polynomial of the cross stream coordinate, which is given by equation 75 here. That means psi is in fact a0 plus a1 psi plus a2 psi square plus and so on plus a n minus 1 psi power n minus 1 plus a n psi power n. So where a0, a1, a2 etc. an are constants, and that can be determined from the boundary conditions imposed. So note that the value of the stream function psi for a given xi represents the volume flow rate between the axis of symmetry and the surface where xi is constant. So to determine these constants, the velocity boundary conditions, as I said, can be used. For an example, on the axis, if you take the axis, xi is 0 and therefore phi is also 0, and that gives a0 as 0. Similarly, in terms of the stream function, the axial velocity can be written as, that means Vz is equal to 1 by r deva phi by deva psi by deva tau, and that is can be further extended as 1 by r deva psi by deva xi multiplied by deva xi by deva tau, and that can then be the dye function can be introduced, then that becomes 1 by r deva phi by deva xi multiplied by 1 by r theta rz, sorry, and that is shown in equation 76. So using the conditions that rz is equal to r1 at z is equal to 0, that is at the entry of the dye, at the entry zone, the velocity boundary condition given by this equation 75 and 76 therefore becomes what? It becomes V0 is equal to 1 by xi r1 square multiplied by a1 plus 2a2 xi plus 3a3 xi square plus and so on, and this is what this velocity boundary condition is given in 77. Because V0 is 0, V0 is constant for all values of xi, and because it is independent of the z value, therefore a1, a3, a4 and etc. including an is 0, and therefore a2 is determined as what? It is determined as V0 multiplied by r1 square by 2, and therefore the stream function which was previously shown, it is shown in 79, it can be simplified to psi is equal to V0 r1 square xi square by 2. The velocity component of this, that is Vr and Vz, can now be obtained in terms of dye profile, that is Rz, from the spatial derivatives of the stream function. That means Vz is equal to 1 by r deva psi by deva r, and that is again equal to V0 by Rz square multiplied by r1 square, and Vr becomes equal to 1 by r deva psi by deva z, and that becomes equal to V0 r1 square xi and rz divided by rz prime divided by rz square, where rz prime is derivative with respect to z of rz. So that means it is equal to d by rz divided by dz. Since the velocity field is derived from the stream functions, that is psi, it automatically satisfies the incompressibility condition and the velocity boundary condition as well. So thus the assumed stream function leads to a kinematically admissible velocity field, and that is what is the condition required in upper bound. So at the plastic boundaries, both the boundaries, that is S1 and S2, the tangential velocity may be discontinuous when the die surface slope at the entry or exit sections happens to be non-zero. Since all the unknown constant in the expression for psi as shown in equation 80 have been determined as usually, if you look back from the velocity boundary condition, there is no need now to use the upper bound theorem, and therefore one can pass through from the velocity field equation, that is equation 81 and 82, the non-zero strain rate components can be calculated. So then it is the non-zero strain rate components is calculated as, that means epsilon rr dot will be equal to simply deva Vr by deva r, and that becomes equal to V0 r1 square multiplied by r prime z divided by r cube z, and similarly epsilon theta theta dot becomes Vr by r, and that becomes V0 multiplied by r1 square multiplied by r z prime divided by r cube z, and then epsilon zz dot becomes deva Vz divided by deva z, and that becomes equal to minus 2 V r1 square multiplied by rz prime divided by r cube z, and similarly epsilon rz prime dot, that is the rate, is equal to half of, that is deva Vr by deva z plus deva Vz by deva r, that is the, and that comes out to be V0 by r z cube multiplied by r1 cube multiplied by r, and in bracket the two corresponding terms, when we expand it becomes r double prime z by 2 minus 1.5 r prime square z by rz, where r double prime, as I said, it is the double differentiation, that is r double prime z is deva d2 rz by dz square, that is the second derivative. So it can be seen that all the strain rate component that we have calculated except epsilon rz dot are uniform over the cross section. So the generalized yield stress, that is sigma bar, at any point is calculated using the value of generalized strain, that is epsilon bar at that point. This is quite usual. The value of generalized strain in deformation zone is therefore obtained by integrating the generalized strain rate, that is epsilon bar dot along the streamlines, while the generalized strain rate, that is epsilon bar dot, is obtained from the proposed strain rate field. If you look at the figure equation 88. So, the streamlines are given by equation 74. So, along any streamline if we take, dt becomes equal to dz by vz and that is equal to dr by vr. This has been shown in 85, and the generalized strain then can be calculated as, that is equal to over the integral, that is generalized strain rate divided by Vz dz. So, that is the simple form. By integrating the strain rate, generalized strain rate, one can get the generalized strain, which is shown here in equation 86. Since the material enters the die as a rigid body, the generalized strain is taken as 0 on the boundary S1. You look at figure 15 again, and integration of therefore the equation 86 is performed using Simpsons rule. One can use the Simpsons rule to obtain the cumulative generalized strain along each streamline. So, from the proposed velocity field and the strain rate field, the equation, and using equation 81 and as well as 84, and the calculated generalized stress field, the extrusion power and the available average extrusion are required, average extrusion pressure can be very well evaluated. So, how can it be evaluated? So because this power would be, can be in three part. That is, the first, there is a deformation during the die region, so that will be have a internal power of deformation. Secondly, at the entry discontinuity section and the exit discontinuity section, there also there would be power loss. So, we have to find out the power because of the discontinuity, and then at the surface S3, along the surface there is a friction, so the frictional losses. So, if you add all these three or four rather together, one can get the total power. So, let us see how can we calculate the internal power of deformation. So, by considering an element of volume dV, small dV, in the deformation zone, which is subjected to a stress system sigma ij, which cause strain rate, that is epsilon ij dot, the incremental power of deformation can be calculated. It can be calculated as, that means d phi p, that is the incremental power of deformation, d phi p will be equal to simply derivative part of the stress tensor, that is sigma ij prime multiplied by the strain rate tensor, that is epsilon ij prime multiplied by dV, because volume is dV. So, the total power of deformation, that is phi p, can be obtained by integrating the equation 87 over the entire volume of the deformation zone, that is has been shown previously, and that comes out the integral over the domain sigma ij prime multiplied by epsilon ij dot dV, and that is because sigma ij prime, when you ignore the hydrostatic part, it can be taken as equal to generalized stress multiplied by generalized strain rate dV. Then secondly, the frictional power, if we calculate, if the frictional resistance of the material along the die work interface is say tau, and the slip velocity tangential, that is the tangential velocity discontinuity along the interface, say it is Vs, then the incremental frictional power of the interface can be evaluated, and it can be calculated as d phi f, which is equal to tau divided by Vs, tau multiplied by Vs mod, the positive value of Vs, multiplied by ds, that is the surface area, a small area ds, where the ds is an elemental surface area. The total frictional power can be obtained by just integrating the whole equation 89 along the total surface interface length, and it is shown here in 90 as over the surface S, it is tau mod Vs ds. So capital S is the area of the tool work interface here. So assuming the frictional resistance on the interface to be constant times the yield shear stress, that is sigma bar by root 3. So one can find out the frictional resistance as M. M is the frictional factor and multiplied by sigma bar divided by root 3. So this value is taken, that is the value of M is taken on the basis of die work interface and the lubrication conditions. One can, for the cold generally it is taken as less than 0.1, and that is how one can choose 0.1 to 0.2 also sometimes. The friction factor in fact varies from 0 for frictionless condition to unity for sticking condition. So the friction factor is however assumed to be independent of slip. This is assumed. So the fourth one that we need to find out the shear power. In case the die profile has non-zero slope at the entry and exit section, there will be power loss due to the velocity discontinuity. So this power, these discontinuity velocity, so the planes of discontinuity can be called the plane of sudden shear. So the power dissipated along these surface can be calculated by implying the yield shear stress as the material resistance. Thus the shear power, that is phi s, can be expressed as over the integral over the surface S, that is sigma bar divided by root 3 multiplied by mod Vs ds, that is shown here in 91, where Vs is the tangential velocity discontinuity along ds and capital S is the area over which the integration has to be carried out. So these four power that we have calculated now, one can sum up for the total power. That means the total power phi would be the sum of the its constituent that we have just calculated, and then it can be written as that phi is equal to phi p plus phi f plus phi s. So internal power of deformation, frictional power and discontinuity power. So in the calculation of the total power phi, the integer, the integral that was calculated earlier, especially in equation 88, 90 and 91, can be evaluated numerically because of variation in generalized stress and shear velocity, and then the average extrusion power can be evaluated. Once the total power is calculated as phi, the average power can be calculated as P average, which is equal to phi divided by pi R1 square V0, and this is what has been shown in 73. So this example gives the 3D case where the hodograph was not required at all because of the geometry, because one has taken care of the streamlines, and the streamline was put into a equation that is RZ. So that's the application of upper bound for 3D situation. We would be taking one more lecture next time to illustrate another a 3D upper bound solution for much complicated situation, and rather it is a generalized case. So with this we would continue in the next lecture for the generalized case of upper bound for 3D case, especially for extrusion, cold extrusion case. So I thank you all for your patience, and I hope that you will give again the feedback to improve upon. I thank you very much again. Thank you very much.